Number 1, 500 draws made at random with replacement from a box of 276 tickets, which are positive. Someone tells you that 50% of the tickets in the box show positive numbers. So the null is that the percentage is equal to 50, and the alternative is that the percentage is greater than 50. So whenever you create SDs, if you can use the box to create the SD, then you do. If you can't, then you use the sample. And in this case, we think the box is 50% positive and 50% negative. So our SD is going to be the square root of 0.5 times 0.5, which is 0.5. And then we create an SE by dividing that by the square root of the number of draws. The reason we have to bring the draws in is the more draws you make, the smaller your error is going to be. So 0.5 divided by the square root of 500, nope. And we get 2.23, which means on my normal curve, we expect 50 to be in the middle, plus or minus 2.23. Well, when we did the sample, we had 276 out of 500, which is 55.2%. So when we put 55.2%, we need to shade to the right and see what the p-value is. So 55.2 minus 50 is 5.2. Divide that by 2.23, and I get a z-score of 2.33. So I shade norm from 2.33 to 5. So 2.23 to 5. Now, we already know the answer. Is this going to be bigger or smaller than 5%? Smaller. Bigger or smaller than 1%? Bigger. Why? 2.23 is between the 5% mark at 1.64 SEs and 2.78 SEs. And looking there, we get 1.2%. So my p-value is less than 5, which means I reject the null, accept the alternative hypothesis, and I say it's significant. So I believe that the true average in the box is significantly greater than 50%. I don't know how much greater it is. I could set up a confidence interval to tell you about where I think it is, but I do not think that this result is due to chance. All right. Any questions on that? Number 3. The Gallup poll asks respondents how they would rate the honesty and ethical standards of people in different fields: very high, high, average, low, or very low. The percentage who rated clergy very high or high dropped from 60% in 2000 to 54% in 2005. This may have been due to scandals involving sex abuse, or it may have been chance variation. A. Should you make a 1-sample or a 2-sample z-test? 2-sample. How come? We want the difference. So that would be, and we took 2 samples. That really is the reason. Formulate the null and alternative. So the null says that the difference is 0, and the alternative is that the difference is greater than 0. And can the difference between 60 and 54 be explained by chance? So we have 0.6 on one side and 0.5 on the other. And how many draws did we do? 1,000. So in both cases, D is 1,000. So the SD is the square root of 0.6 times 0.4. So the square root of 0.6 times 0.4, and I get 4.89. So I guess 60% is the breaking where you don't get 4.99 anymore. So 4.489, which is basically 0.4. No, we're going to do 0.49. Okay. And then over here, when I do the square root of 0.5 times 0.5, I just get 0.5. Now to create an SE, I need to divide each by the square root of 1,000. So 0.49 divided by square root of 1,000. And then I do the exact same thing with 0.5. And on one side, I get 1.55. And on the other side, I get 1.58. What do I do with those two standard errors? Create the SE for the difference. I square root the square of both of them. So the square root of 1.55 squared plus 1.58 squared, and I get 2.21. Now what do I do? I need to create a z-score. Because this is a two-sample z-test, I subtract the expectation on both sides, and I expect the difference to be 0. That's my null hypothesis. And when I subtract 50% from 60%, I end up with 10%. So 10 minus 0 is 10. And then I divide that by 2.21. And I get 4.51. Should I shade norm with 4.51? No, I'm going to get a number that's very, very close to 0. So if my p-value is essentially 0, then I reject the null and accept the alternative, and I say there is a highly significant difference between the value of 60 and the value of 50. So do I think that the, what did they call it? Do I think that the ratings of clergy went down? I do. Now, can you think of a scenario where I get 60 on one side and 50 on the other, and then I accept the null? What would have to happen in order for me to accept the null with a 10% difference? What would need to change? The number of draws. So with 500 draws, a 10% difference is highly significant. But if I only had 50 draws or 12 draws, then 10% might not seem like a lot. Because the more draws you do, the more certain you become. All right, number 7. When convicts are released from prison, they have no money, and there is a high rate of recidivism. And in our area, people drive down I-70 and get picked up for drugs, and they live in San Diego or they live in Wisconsin, and they go to jail, and when they're released, they get let out of their cell, they pick up their stuff, they walk outside the door, and they're in the wrong state with no money and no car. Well, they might have money, but their car has been impounded. What do they do? Well, luckily in our area, we have groups that will buy them bus tickets to wherever they need to go. So that's kind of nice. You can if you can afford it. But if your car is full of drug money and drugs, you lose both. And so when you leave, you have no money and no car. So it's a huge problem. These people don't have anywhere to go. So we do what we can to help them get home. Um, so the released prisoners return to crime and arrested again. So if you're, I mean, let's say that you're a really bad person and you step out of the jail and you have no money and no car, what are you going to do? You're going to find the car and drive it home. I don't know. I mean, that's what this is kind of implying. They return to crime and are arrested again. Would providing income support to ex-convicts during the first months after they were released from prison reduce recidivism? So if we start helping these people financially as soon as they get out, are they less likely to come back? And in the long run, it might save us some money. So putting somebody in jail is really expensive. So if putting them in jail for a certain amount of time costs $30,000, what if we could use $5,000 to help them find a place to live, help them get a job with that sort of stuff? Then we spend 5 instead of 30, and we never see them in jail again, and they're going to be much happier. Does it work? So the Department of Labor ran a randomized controlled experiment to find out. The experiment was done on a select group of convicts being released from certain prisons in Texas and Georgia. Income support was provided, like unemployment insurance. There was a control group which received no payment, and 4 different treatment groups differing slightly in the amounts paid. So basically, the insurance says, if you are actively looking for a job and you meet these qualifications, we will pay you if you cannot find a job. We will help you live financially as long as you are actively looking for a job and meeting all of our qualifications. Whereas the other people just got released like they normally do. Do you think it helped? Well, let's see. The exercise is on the results from Georgia and combines the 4 treatment groups into one. So instead of looking at all 4 payment plans, we're just going to say either you received financial help or you didn't. 592 prisoners were assigned to the treatment. 48.3% of them were arrested again within a year of release. Ouch. That's a lot of people. So 592, and we had 48.3%. Okay. 154 were assigned to the control group, and 49.4 were rearrested within a year of release. What do you think? It didn't help a lot, a little bit. So I guess what you'd have to do is see if it's statistically significant, and then figure out how much money did you pay and how much did you save by not putting those few people back into jail. All right. So my SDs are going to be 0.499 in both cases. Everybody agree? Okay. So my SE is going to be 0.499 divided by the square root of 592, and 0.499 divided by the square root of 154. So 0.499 divided by the square root of 592. Wait a minute. Do you follow? I don't want to put your name on the video. You get what I'm doing? I'm going fast again. Okay. Good. So this is 2.05%. Okay. And then 0.499 divided by the square root of 154, and I get 4.02. Now, wait a minute. The percentages are the same. Why are those so different? There are a lot more people in the treatment group than in the control. All right. So I draw my normal curve. I put 0 in the middle. That's my null hypothesis. The actual difference is 1.1. Now I need to divide that by the SE for difference, which is going to be the square root of 2 squared, which is 4, plus the square root of 4 squared, which is 16, and I get 4.4. So my SE for difference is 4.4. So I put that here. 1.1 divided by 4.4 is 0.25. How much area is there to the right of 0.25? A lot, like 40% or something. So we accept the null and we say this particular program did not help, which is really sad. I mean, you hope that it would, and maybe there was something wrong with the program. I don't know. But there is no statistical difference between the control and the treatment. B, in the first year after their release from prison, those assigned to the treatment group averaged 16.8 weeks of paid leave. The SD was 15.9 weeks. For those assigned to the control group, the average was 24.3 weeks and the SD was 17.3. Did income support reduce the amount of money that ex-convicts worked? So they said, okay, it didn't stop people from making it back into prison, but maybe it still did some good. So in the treatment group, the treatment had 16.8 weeks of paid work, and the SD was 15.9. And this was 592 people. And then for those assigned to the control group, the average was 24.3 with an SD of 17.3. That's my SD, and there were 154 of these. Okay, what does that mean? What are they looking at here? Does anybody understand what these weeks are talking about? So at the end of 1 year, they ask everybody, how many weeks in the last year did you have a job that paid you money? Not community service, but a job that paid you money. The average for the people that were given financial assistance was 16.8, and the average for people who received no assistance was 24.3. So what does it look like the financial assistance did in this study? It actually seemed to make them work less. Well, let's run the numbers because well, what do you think? Do you think that's statistically significant? It's quite a bit. So I would say yes, those SDs are both pretty high. So we're going to have to run it to see. So I'm going to take 15.9 and divide it by the square root of 592. And I get 0.65. So my SE is 0.65. And then I take 17.3 and divide that by the square root of 154. And I get 1.39. Now what? SE difference, which is basically the Pythagorean theorem. So we do the square root of 0.65 squared divided by 1.39 squared. And I get 0.46. Nope, that doesn't make any sense. Oh, I didn't add them. How did I know that wasn't right? It's smaller than both of them. The SE difference has to be bigger than the average, but smaller than the sum. So I need to go through here and change that to a plus. That looks better. So my SE for difference is 1.53. So my null hypothesis says the difference is 0. The actual difference, 24.3 minus 16.8, which is 7.5. So This line here is resting at 7.5. What is that in terms of standard error? So 7.5 divided by my SE difference of 1.53 is 4.9. Is there any reason why we should shade from 4.9 to 5? No, the answer is going to be 0.00001 or something. Essentially, it's 0. So we reject the null, and we accept the alternative hypothesis, and we say there is a highly significant difference in the amount of work these people did for money 1 year up to 1 year after they were released, which shows us the program didn't seem to help. Now, there are other things that it might have benefited, right? It didn't ask what was your work for employment. Well, if selling drugs was your work, that's probably not good. So if convicted drug dealers stop dealing drugs because we help them find a better job, that would be a good thing. So these two problems we did do not necessarily say that the program is bad. Right. It might take longer to go to a CDL class and be trained and then get a truck driving job. And that might be a lot better than racketeering at, in some organized crime group. So we can say people did not get arrested less when we help them financially. We can also say that as far as paid work is concerned, the financial assistance seemed to hurt. But there are a lot of other things going on in here. So you're talking about, if you hadn't asked me, I'd have been able to tell you. Oh my goodness, guys, help me out. They're called, there might be a third. They probably what? We don't know. And that's the thing. Are they telling the truth? Yeah, we don't know. We don't know if they're telling the truth or not. Why can't I think of the, what is that called? So what chapter was that in? Was it 6? Not measurement error. It's probably the name of one of the chapters. Confounding factors, confounding variables. Yes, there may be some bias and some confounding variables in here. So one thing that this points out is if the news reports on this, they're going to say financial programs fail. Right? That's going to be the headline. Or, so that would be the first one. Or financial programs do more harm than good. So the problem for A, it didn't work like we wanted it to. And in B, it seemed to be bad, which we didn't expect. But again, there are so many other things going on. Did these people get a job working at a fast food restaurant for minimum wage? And did these people get nice careers that they could support a family with? If that were the case, then it might be worth it. Recidivism. Right. So if we go back to the other one, half of them went back to prison. But if that's going to happen anyway, and we can get 25% of the people to get good jobs, that might be worth it. Right? If we can improve 25% of the people who leave prison, if we can make them more successful, it might be worth it. So anytime, and we talked about this clear back in chapter 1, anytime you crunch a situation down to one number or one answer, you are totally misrepresenting the whole picture. So it's really, really complicated. All right, number 8. All right, 27. I lost my page, sorry. Number 8. One experiment contrasted response to prediction request and to request only treatments in order to answer two research questions. 1. Can people predict how well they will behave? And 2. Do their predictions influence their behavior? In the prediction request group, subjects were first asked to predict whether they would agree to do some volunteer work. Then they were requested to do the work. In the request only group, the subjects were requested to do the work. They were not asked to make predictions beforehand. In parts A, B, and C, a two-sample z-test may or may not be legitimate. If it is legitimate, make it. If not, why not? Okay, this is going to be fun. I wish we had answers. 46 residents of Bloomington, Indiana were chosen at random for the prediction request treatment. They were called and asked to predict whether they would agree to spend 3 hours collecting for the American Cancer Society. If contacted over the telephone with such a request, 22 out of the 46 said they would. Another 46 residents of that town were chosen at random for the request-only treatment. They were requested to spend 3 hours collecting for the American Cancer Society. Only 2 out of the 46 agreed to do it. Can the difference between 22 and 46 out of 46 and 2 out of 46 be due to chance? What did the data say about the research questions 1 and 2? So I believe they're independent. They're totally different people. So we would need to do it. So this would be a t-test. Yeah, there are only 46 draws. Wow, it doesn't have us do it. We didn't read anything about a two-sample t-test, right? Maybe it just wants to run it with a z-test and just see what happens. Yeah, do we really want to work this one? Okay. Number 8 has been removed. Sorry. Sorry, no number 8. So, well, and maybe it'll be valuable to go through there. Those are independent. The first group has nothing to do with the second group. Right? Okay, 3 days later, the prediction, we're just skipping, we're done. We're going. What's the next one? 10. An investigator wants to show that firstborn children score higher on IQ tests than secondborns. Uh-oh, I'm a secondborn. He tests a simple random sample of 400 two-child families at a school district, both children being enrolled in elementary school. He gives these children the WIC vocabulary test with the following results. The 400 firstborns averaged 29 with an SD of 10, and the 400 secondborns averaged 28 with an SD of 10. Scores are corrected for age differences. Does that make sense? A first grader is not expected to do the same as a fifth grader. So they scale their score according to the grade they're in. So he makes a two-sample z-test. The SE for the firstborn average is 0.5. So that would be 10 divided by the square root of 400 is 20, which is 0.5. The SE for the secondborn is exactly the same. So the SE for difference is the square root of 0.5 squared plus 0.5 squared, which is 0.7. And the z-score is 1 because 29 is 1 different than 28. Divided by 0.7, which is 1.4, which has a p-value of 8. So we accept the null, and we say, nope, there is no significant difference between the score of 29 and 28, which means I still have a shot in this world. Okay, now, guess what? That's how statistics really works, right? So what you do is this. You go give the test, okay? And you give it electronically. The kids fill in the bubbles. The computer gives a score. Oh, hold on a second. This is important. So all of the firstborn kids' scores show up in a spreadsheet. And all of the secondborn scores show up in a spreadsheet. So you have 400 scores in each group. What do? You don't compute the average. You don't compute the SD or the SE or the SE difference or the z-score or the p-value. All you do is tell the computer, hey, I have 2 samples. Tell me what the 2 sample z-score test statistic is. And it goes through and it spits out the averages, the SD, the SE, the z-score, and the p-value. And then all you do is look at the p-value and say, oh, 8%. Huh, looks like it didn't help. That's what statisticians do. They design the experiments, and then you have to look at the situation and you have to choose the correct test. So you just scroll down and you say, hey, computer, 2 sample z-test. Or if there aren't very many draws, 2 sample t-test. And it does it all for you. You don't compute anything. All you do is interpret the results. All right, is that the last one? Okay. Are we